Hey everybody, we're going to be going over some of the horizontal projectile problems. So, here we go. If you want to skip around, I'm going to go over some of the basic fundamentals in the beginning, and then there will be timestamps below. You can click to go to the different examples, right? All that good stuff. So, right here, we are looking at the basic design of what motion graphs look like. And this would be for something that's traveling in the what we would call the positive horizontal direction, right? And the way we know that is, here we have this X position graph, horizontal position, and it's got a positive slope that tells me I have a positive velocity. And when we look at these motion graphs, any projectile anywhere in the known galaxy, pretty much, for everything that we know, the motion graphs for a projectile should look just like this. Okay, now the values might be a little different, right? The acceleration on different planets will be different, but the shapes, the behaviors of how a projectile flies through the air should be the same. So if we look at rules for all of our projectiles, okay, there we go. All of our projectiles, we can figure out that if this is what all of our projectile motion graphs look like in the x direction, then the x velocity is always constant. All right, so in other words, it never changes. So what that does is it tells me the acceleration in the x direction is always equal to 0 meters per second squared. Okay. On the flip side, if we look at the vertical direction right there, then I can get an idea that in the vertical direction, right, this slope of the position graph is changing. So my velocities are always changing. Okay, so the in the y direction, the velocity is always decreasing. And what do I mean by decreasing? Decreasing, if you take a look at this velocity graph right there, it starts here, and over the course of this graph, notice this is always going down. So that's all we mean by decreasing. The velocity is always changing negatively, right? And so what that does is it tells me there is always a negative acceleration. Because remember, acceleration is simply the change in velocity over time. So this tells me acceleration in the y direction is always constant. And we can actually figure out what that acceleration is by looking at the slope of this velocity graph. But on Earth, right, acceleration in the y direction on Earth is usually about what we would say negative 9.8 meters per second squared. And again, that's on Earth. All right. So these are kind of the rules that we govern all of our projectile stuff from. And so let's get into some problems. Take a look at it. All right, this is one we did in class yesterday. But the movie The Gods Must Be Crazy begins with a pilot dropping a bottle out of an airplane. Let me see if I can get that right there. There we go. A surprised native below who thinks it's a message from the gods recovers it. This is an actual movie, by the way. You can look it up if you want. It's a classic. If the plane from which the bottle was dropped was flying at a height of 500 meters, so right away I'm thinking that's important, and the bottle lands 400 meters horizontally from the dropping point, how fast is what it's asking us was the plane flying when the bottle was released? So I'm going to draw a picture to start, okay, just to get an idea of what's going on. So we have a plane. Right? You never pass up an opportunity to draw a picture. And we have a bottle. And this bottle gets released, and this plane is going to the right with some velocity, which means that the bottle, when it gets let go, has that exact same vertical velocity. Right? And it even says that pilot driving bottle is flying, ball lands 400 meters. Okay, we know the bottle was dropped, so we know that all of the velocity is in the x direction. And if this bottle goes, follows a parabolic path down to the ground, this is basically what that looks like. And I can draw what else I know on here. I know the bottle falls. I need to make that skinnier. There we go. I know it falls 500 meters. And I know that this bottle goes from where it's dropped to there. It is 400 meters on the ground. Okay, so that's all the information that we have through here. Now remember, our first step after we have our picture drawn is to make a list of all the information that we know. Right? So the very first thing I'm going to do is, this is a two-dimensional problem, which means I'm going to have values in the x and y direction. So I'm going to make a t-chart right there to keep track of them. And now we can do that. So I know from the rules of projectiles, I know the acceleration in the x direction is always 0. And I know the acceleration in the y direction is always negative 9.8. Because I'm kind of guessing that this problem is taking place on Earth. Okay, like most of our problems will. What else do we know? We know the displacements. Right? I know that this bottle goes horizontally 400 meters. So there, and I know that vertically this bottle falls down at 500 meters, so we put negative 500. And then what else do we know? We know the initial velocities, right? I don't know what the x direction is. In fact, that how fast part in the x direction, that's ultimately what we're trying to solve for. And then in the y direction, that would be 0. It is 0 because if this bottle is dropped, if you take a look right there in the picture, we have all of that bottle's initial velocity in the x direction, which means it starts with 0 in the y. Okay. Now, we don't have enough here yet to be able to solve for our problem. And I'm actually going to go grab some equations. And there they are right there. And we have these equations to choose from. And so I need to pick which direction do I know enough info to solve for this. And it's an X type of question right there. And so I need to only use the X direction to solve for that missing value. Well, in the X direction, I don't have enough. Right? I only have, let's see here. There we go. I only have 2 things. And so that's not enough to use any of these equations. So I have enough in the y direction to possibly solve for something, but I don't know. So here's a common trick, if you want to call it that. There is one variable that we have that can be shared between both the x and y direction, and that is time. Okay, time is the one thing that will be the same here as it is here in the x and the y. So a common trick is maybe I can solve for time using all of my y numbers right there, and then I'll have enough to solve for that velocity in the x. So let's do that. So I will, let's zoom in a little bit. Okay, solve for time using the y direction. And I'm going to scroll down just a little bit. So I need to pick out of all these y values, I need to pick which equation I'm going to use to solve for this. So I need an equation that has all 4 of these variables in it. And that's going to be my second equation right there. Okay, so I'm going to go back over here. Let's keep everything nice and color coded. So I'm going to say delta y is equal to initial velocity time. And remember, my goal right now is to solve for time. So first thing is, if you have any values that are 0, just plug in the 0 to make your life easier, right? The initial velocity in the y direction was 0, so if I plugged in 0 right here, this whole chunk would go away. And so I like doing that first. And so I'm left with this. Now I just need to get this time variable all by itself. So multiply, I'm going to get rid of this fraction first. Multiply both sides by 2. That goes away. And then I'm going to divide both sides by a, the acceleration. And then the a's go away. So right now I'm sitting with 2 times displacement over acceleration is equal to t squared. And the very last thing we need to do to get that t all alone, square root both sides. And so we have t is equal to 2 times the vertical displacement over the vertical acceleration. Okay, plug in all those numbers and we get approximately 10.1 seconds. Now remember, that's not the final answer, so we're not all the way done yet. But what I do have now is, take a look. If I go up here and plug in my values, let me zoom out just a little bit. Right, 10.1, 10.1. Remember, time is the only one that can be shared between those two. Now I have enough in the x direction to pick one of these equations and solve for the missing initial velocity. Okay, so that's what I'm going to do. I need to take a look. I have the same variables available to me, so it's going to be the exact same equation again. Okay, what color should we use? We'll use white. And zoom in a little bit, and we got, now solve. So now I'm in the x direction. Initial velocity time plus 1/2 at squared. Remember, that initial velocity is what I'm trying to solve for. And the acceleration in the x direction is 0 right there. So right away, if I plugged in 0 to that piece, this whole chunk would go away. And so we're left with delta x is equal to initial velocity times time. I'm trying to get that initial velocity by itself, so divide both sides by the t. And we're left with that initial velocity is delta x displacement over time. Well, we know the thing went 400 meters in about 10.1 seconds. So if it went 400 meters in 10 seconds and it was going the constant velocity the whole time, then I know this was about 39.6 meters per second. So it goes right under 40 meters every single second this thing is falling through the air. So that right there is our answer. Happy days. Okay. Now you'll notice as we go through these problems, a lot of the processes are the same. So that's really what you want to have stick in your brain. Not just, you're seeing these being done and you're wanting to find the pattern or the routine, the rhythm to getting these projectile problems done. So here's our next one. Suppose an airplane flying 60 meters per second at a height of 300 meters dropped a sack of flour. So it's flying that fast. It's that high. Drops is an important word. Remember, that dropped word tells me that the initial y velocity is 0. Okay, how far from the point of release would the sack have traveled when it hit the ground? So we got another plane flying. Wonderfully drawn plane right there. Sack of flour. And it goes, that's a terrible parabola. Hits the ground. Okay, now what do we know? We know that this bag is going at 60 meters per second horizontally. We know that it is at a height of, looks like 300 meters. And we know, that's about it. Okay. we are being asked to find this displacement. How far from when it's dropped is this going to go? So remember our steps. Let's make a list of all the quantities and info that we know. X, Y, this is a two-dimensional problem. I know the acceleration in the X is always 0. I know the acceleration in the Y on Earth is always negative 9.8. Okay. I know displacements. Well, in the X direction, that's what I'm trying to solve for. So I'm going to put a little question mark. In the Y direction, I know this sack of flour fell, so negative 300 meters. And then, let's see, we know initial velocities. In the X direction, this thing was flying at 60 meters per second. So that's what the bag leaves the plane with. And in the Y direction, this was dropped, right? So if it's dropped, that tells me that the initial Y velocity is 0. Okay, so this is pretty similar to last time. We're just solving for something different. I don't have enough to solve for anything in the X direction yet. But what I do have is I have more information in the Y direction, so maybe I can solve for time. Get time in the Y direction, which means I can use it in the X. Okay, so I need to pick an equation. Lo and behold, it's the exact same equation we were using last time. So all right, let's do it. Delta Y is equal to initial velocity t, 1/2 at squared. I know the initial Y in this problem was 0. In this problem, I'm solving for t again. So just like last time, if you want to see this worked out, you can skip to the previous example. But we have t is equal to the square root. And I set that equal to. Plug in all my numbers. It falls 300. That is over negative 9.8. I don't know what that is because I haven't done any of these problems ahead of time because I'm just doing it right along with you. 600 divided by 9.8. Square root of 61.22. 7.82. That's with a lot of rounding. So about 7.82 seconds is the time that that bag is in the air. So we go and put it up here. $7.82. Okay. Now in the X direction, take a look. We have enough stuff, right? The X direction has enough information there to use one of those equations. So just like last time, with these 4 variables, that's that one kinematic equation we've been using. So let's use blue. Let's get crazy. Okay, now we're going to solve for delta x. This is a really fast one. Because acceleration in the x direction, always 0, so that chunk goes away, right? And now I'm just left with delta x equals velocity times time, which I know those things. 60 meters per second. And the time we just figured out is 7.82 seconds. I don't know what that is off the top of my head. Oop. 60 times 7.82. 469.2. meters. Remember, displacement means that direction matters. This is positive, which means that it was moving in the positive direction, which we usually always say is to the right. So the bag fell from where it was dropped. It displaced another 469.2 meters to the right. Okay. What this... Why are you doing that? Scroll. It's zooming now instead of scrolling. But the other part of this question says, where will the plane be in relation to the sack when the sack hits the ground? And basically, both of these things are going 60 meters per second to the right. Remember, if we drew that vector anywhere on this bag's path, it would always be going 60 meters per second to the right, just like the plane. So 7.82 seconds later, the plane has gone just as far as the bag because they both had the exact same velocity, horizontal velocity. So they've both displaced horizontally the exact same amount. So when the bag hits, the plane should be right over top it. Okay? Oh yeah. It's not scrolling, it's zooming. So let's go over here. 2 more. In many locations, old abandoned stone quarries have become filled with water. While standing on a quarry, a girl tosses a piece of granite into the water below. If she throws the rock horizontally with a velocity of 3 meters per second. No, where's my red? I want red. There we go. 3 meters per second, and it strikes the water 15 meters away. How high is the question? Above the water is the wall. Okay, so draw a pretty picture. Stone quarry. There's water below. Rock gets thrown. It goes parabolic, like any projectile. Pew, psh, splash. It was originally thrown with a horizontal velocity of 3 meters per second. And it strikes the water 15 meters away from where it was thrown. And we are being asked, how high up is this wall? So we don't know, but we want to figure out what is delta y. Okay. Cool. So let's make a table of everything that we know in this problem. This is a 2-dimensional problem. It is moving horizontally as well as up and down. So let's see. I know acceleration for any projectile. Horizontally, the velocity is constant. So I have 0 acceleration in the x direction, negative 9.8 in the y direction because we're on Earth. Let's see, I know initial velocities. The initial velocity in the x direction right there, it said it was going horizontally with a velocity of 3. And in the y direction, if it's all horizontal right there, then that means that there's no initial y velocity. You would also know that because this video is called Horizontal Projectiles. Let's see, what else do we know? Displacement. I know the x displacement is positive 15 meters. I don't know what the y displacement is. In fact, that's what we're being asked to solve for. And that's it so far. Okay. So if you notice, this is similar to the other two, but now where don't I have enough information? I don't have enough information in the y direction, but I have more information in the x direction. So maybe I can solve for time in the x direction. Nope. It's not happy with my clicks there. Oh my God. Whatever. And sorry, I just had to restart it. it's doing it again. Whew. There we go. Similar to the previous ones, right? If I can find time in the x, then I can just share that over with the y direction. Okay, so let's pick an equation. Let's grab this down here, put it here, because I don't know what it is going to be. Looks like the same variables, so we're going to use the exact same equation again. What do you know? This is one of the most widely used equations in kinematics. Okay, so I'm going to solve for time using the x direction. So let's do delta x equals initial velocity times time plus 1/2 at squared. What do we know about velocity? In the x direction, it's always constant. So the acceleration is 0. So this whole chunk goes away. And I'm left with a much simpler looking equation. And I do a little abracadabra. I divide both sides by, not that, v naught to get time. And so I'm left with these canceling. How dare you? Oh my goodness. It's doing it again. Time is equal to delta x over velocity. Well, it went 15 meters. And it was going 3 meters per second. So we do a little math, 15 over 3. That gives me 5. And if you simplify these units, meters over meters per second. I got a denominator in the denominator, right? Fraction in the denominator. This turns into meters times the reciprocal of the bottom. And so, bleep, bleep, our answer is in seconds. Okay, so our answer is in seconds. So I got 5 seconds for each time. Now I know enough in the y direction that I can solve for this missing displacement. And the nice thing is there, I use my equation. At squared. Right? I know initial velocity in the y direction is always, not always, but in this case it's 0. So my equation got much simpler. 1/2 at squared. All I need to do now is plug in my numbers and chug away. So 1/2, negative 9.8. The time was 5 seconds squared. Multiply all that good stuff out. And we get a delta y vertical displacement of 122.5 meters. Okay, now notice this answer would be negative. So what does that mean? That means that the rock fell 122.5 meters down to the ground. Okay, but this is where you'll get some weird things, because like on the AP test, to make sure that like people aren't getting mixed up like that, they would say something to the effect of like, what is the height or what is the magnitude of the displacement, or something of that nature, where you know the answer you're going to do needs to be positive. Okay, so yes, the rock fell 122.5 meters, which is why our answer was negative, because that's a vector and it's a displacement. But your answer to how high above the water is the wall would be 122.5 meters, right? If one of you in class put negative 122, I wouldn't mark you wrong. It's just, it's weird. If I asked, how high is that building? And you were like, negative 60 meters. That's weird. Okay. Last one. Tad drops a cherry pit. Excuse me. Tad drops a cherry pit out of the car window that is 1 meter above the ground while the car is traveling down the road at 18 meters per second. So that's important. That's important. How far horizontally from the initial dropping point will the pit hit the ground? It's kind of like the plane problem with the sack of flour we did earlier, right? I got a little cherry pit. I have no idea what a cherry pit looks like. There. Cherry pit. It gets let out of the car. Sure. There's a car. I don't know why it's so bumpy, but it is. Right? The car is going 18 meters per second to the right, which means this cherry pit is also going 18 meters per second to the right. And then it goes boo and hits the ground. We know this thing is 1 meter above the ground. Let's make our table. I'm going to make it over here. Let's get crazy. What do we know? We know acceleration in the x is always 0 and the y is always negative 9.8. We know initial velocity in the x is 18 meters per second. We don't know, well, I guess we do know. We do know the initial y velocity because it is dropped. The initial y velocity is always 0 for something that is dropped. Let's see, what else do we know? We know the displacement. We don't know the horizontal displacement. That's what it's asking us to solve for. We do know the vertical displacement. It falls down 1 meter. And that's all we know. So it's that trick again. We got to find the time, right? I know more information in the y direction than I do in the x. So that's what I need to solve for first. Okay. Same as before, I have these 4 variables. So the only choice I have when I'm given those variables is the same equation we've been using for all of these. The granddaddy of the kinematics equations, or grandmammy, I don't know. Delta y equals v naught t plus 1/2 at squared. Okay, we need to solve for t. Make your life easy. Plug in zeros where they occur, right? I have 0 initial velocity. So that chunk turns to 0. And like I said before, we have now solved this problem multiple times for time. So if you need to see this worked out, go to the second example, but we do a little abracadabra, solve for time. And then we can plug in our variables. Okay, this is 2 over 9.8. 0.2, and then I can square root that. To give me 0, that time that it takes to land on the ground is about 0.45 seconds. Okay? And so 0.45, that's the same in both of my columns. And from there, now I know enough in the x direction to solve for the missing displacement. Okay? Delta x is equal to velocity times time plus 1/2 at squared. We should be kind of getting the rhythm by now that I have 0 acceleration. So any projectile problem using that formula just kind of simplifies to this. Velocity times time. Okay. From here, I plug in my numbers. It's going 18 meters per second for 0.45 seconds. So that's about half. So it should be just under 9. 18 times 0.45. 8.1. That cherry pit falls 8.1, goes forward 8.1 meters till it hits the ground when they are driving so recklessly at 18 meters per second. I have no idea how fast that is in freedom units. Let's see. Convert 18 meters per second to miles per hour. Oh, I put my phone on silent. But 40 miles per hour. Okay. So it's going about 40 miles per hour. Just a bunch of crazy youths. And yeah, the last question. If the car continues to travel at that same speed, where will the car be relative to the pit when it lands? And remember, the car is also traveling at 18 meters per second. So if we only look at what's going on horizontally, the car is going 18 meters per second, and the pit, the cherry pit, is going 18 meters per second to the right. So in the same amount of time, they're both going the same speed. They're going to both travel the same distance. So the car should be right lined up with the pit still. Cool. All right. Hopefully this helps. I'll try to start doing more videos so we can see, not have to take time in class. But let me know.